Hello, everybody. I'm Serafina, and today I'm going to be talking about dark matter and all of the evidence supporting its existence. I'm also going to talk about possible dark matter particle candidates because at the moment we don't really understand dark matter as a particle. But first, let me talk about myself. As I said, my name is Serafina Rhind-Tutt. I am from Washington, D.C., and that's where I'm presenting from right now. And I'm currently a junior at St. Stephen's and St. Agnes School. For my Polygence journey, my mentor is Sana Bimani, and she's helped me a lot throughout the whole process. And I chose to study dark matter because I have general interest in particle physics and also cosmology, and dark matter kind of combines the two. So, before we really dive in, you need to know that dark matter is non-luminous, non-baryotic matter. So this means that it doesn't produce light and it doesn't act like the matter we're familiar with. So it doesn't act like you or me or this table. It doesn't interact with the strong force at all, and it makes it real excuse me. It makes it really hard to see on macro and micro scales. But we do have observational evidence that allows us to see some interesting behavior. So, to start, galaxy rotation curves are curves of the measurement of velocity of an individual galaxy versus the velocity versus the distance from the center. So, on the x-axis, you can see the radius, and then on the y-axis, you can see the orbital velocity. Velocity. Kepler's law predicts that as you get further from the center of a galaxy, the velocity should slow down. And this is what this blue line represents, the expected velocity as we get further from the center. But the green line is what we actually measure. And so it kind of does go down in velocity, but it tends to plateau out instead of curving down like we would really expect. And this is because that there is more mass in the system than we can see, which kind of slows everything down as a whole. And this mass is dark matter. Um, Gravitational lensing. Gravitational lensing happens when a light is shining onto a massive object, and the more massive the object, the more bending of the light there is. So, when light shines onto a galaxy cluster, more light is bended than we would have expected. And we can also apply this to the bullet cluster. And the bullet cluster is a really interesting phenomenon where two galaxy clusters collided. So hundreds to thousands of galaxies were colliding together. And you can see that in this photo, the sheer number of galaxies. So, when the two clusters collided, scientists saw a lot of X-ray gas emissions in the center of the collision. So, this led them to believe that this is where the bulk of the matter was. But using gravitational lensing, they saw that the majority of the matter was still sitting on the outskirts of the collision, and it was matter that we couldn't see. So, this not only proved again that dark matter does exist, but it led us to believe that dark matter has the ability to go through itself. So normal matter can't, so it kind of gets stuck in the middle of the collision, but dark matter can, and it's able to go through and end up on the outskirts. Um, Next is the cosmic microwave background. And this is a really complicated topic, and it could be a project in and of itself, so I'm going to simplify it as much as I can. But basically, the cosmic microwave background is relic radiation left over from the Big Bang. And it kind of works like a baby photo of our current universe. And when we're looking at the CMB, we're looking at the highest energies of our universe. And this information has allowed us to understand that 95% of all matter in the universe is dark matter. So it's really abundant. Um, yeah, yeah. So if we look at the photo, we can see that the red represents the hot temperatures and the blue is kind of representative of the cooler temperatures. This is the photo of the CMB in temperature. And these warm temperatures are correlated to the over and under densities in the early universe. And these will eventually become the seeds for galaxy clusters. So they'll eventually evolve into just thousands of galaxies. But like gravitational lensing, the CMB tells us about dark matter's behaviors. When we look back in the early universe, we can see that ordinary matter interacted with light. And this meant that it got pushed around a lot, it moved around a lot, but dark matter didn't move at all, which proves that it doesn't interact with light at all. And then to go into the particle side of things, the standard model of particle physics is really important to understand the dark matter issue because basically what the standard model of particle physics says is that all matter is made up of different elementary particles. And this is kind of what this photo up here is saying, to the right is saying. The outer circle is fermions, which are the elementary particle for matter, and then the inner layer are the bosons, which are the force carrier particles. But there are some limitations to the standard model of particle physics. It cannot explain what gravity boson is, and it cannot explain what dark matter's elementary particle is. And since dark matter makes up so much of our universe, it really is a big issue that we don't really know what it's made up of. Personally, I studied three different possible dark matter candidates, machos, WIMPs, and axions. Machos are massive astrophysical compact halo objects, and these are basically objects that don't produce enough light compared to their mass. So this would be things like white dwarfs. Machos, however, have been kind of ruled out as a particle candidate because as telescopes have developed, we've seen machos and we've seen that they don't exist in enough abundance to really explain the dark matter issue. WIMPs, on the other hand, were theorized to explain one of the other issues within the standard model of particle physics, which is known as SUSY, or the supersymmetric problem. Again, I don't really have time to explain that. But in order to solve this problem, WIMPs would have to exist in extreme abundance. So there would have to be millions and millions of WIMPs. But we have still been yet to discover them. And this leads us to believe that WIMPs do not exist because if they did, they would exist in extreme abundance and we would have already found them. Lastly, the axion, unlike its predecessors, is an extremely light particle. So machos, you can see massive, and WIMPs, they're massive. So the axion is really different from its predecessors. It's a really light particle that was created to solve a problem not within the standard model, but beyond the standard model, known as the charge parity problem. And right now, it's the most popular theory because there's nothing proving it incorrect. Though some theorize that we have dark matter completely incorrect and we kind of just need to start on a blank slate. If we are looking at particle candidates, axions is probably the most popular. It's still yet to be discovered, so we are working on trying to discover axion as a particle, but that's all I have. Thank you.
Serafina, thank you so much for that presentation and for giving us an overview of so many great topics. So, any questions from the audience or the panelists? Well, while others think about their questions, I have a question. So you mentioned that in a galaxy, the speed goes down as you go further out from the galaxy, right? But
Yes.
the curve, if you went very close to the y-axis, there was actually initially an increase before it went down. Is that something you understand?
Yeah, this is basically just because when you're really close to the sun, there's not a lot going on. There's not a lot of stuff there. And it doesn't spin as fast because Kepler's law, if you look at the equation, it really just enacts a little bit farther out and then it kind of goes really high, it reaches its peak, and then it kind of climaxes out.
Got it. That makes sense. Yeah.
Hmm.
You also mentioned the cosmic microwave background radiation. Um, So you mentioned that this is like a baby photo of the universe. Can you say more? That was a very interesting metaphor.
Yeah. So the way I see it is when I hold up a baby photo of myself, you can kind of see the similarities. You can kind of see where stuff is going on, but stuff has changed and it's kind of developed. So like I was talking about the temperature fluctuations, where it was hotter, there was over densities, and where it was colder, there were lower densities. And these temperature fluctuations kind of evolved into the galaxy clusters. So it kind of just got bigger, it changed, but it's still very similar.
Yeah. Um, and can you give us a sense why it is so important to understand this darkness that's in the universe and that we have a hard time making sense of?
Well, as I've mentioned, it makes up so much of our universe. 95% of all matter is dark matter. And it has these weird behaviors. Like it doesn't interact with light, it doesn't interact with the strong force. So once we understand that, we'll be able to understand other cosmological issues.
Got it. Um, any questions from the attendees or the panelists? I have more questions. Ooh, I just got two questions. Would neutrinos count as an axion?
Well, neutrinos goes back to the standard model of particle physics. It's a type of elementary particle. So, no, those have kind of been ruled out as dark matter candidates.
Yeah, great. Yes. So this attendee also continued the question that they heard that dark matter is made of neutrinos. So is that correct?
So, from my understanding, no, because neutrinos are like they're a type of fermion, so it wouldn't really be an issue with the standard model of particle physics to understand what dark matter is if they were neutrinos.
Makes sense. Serafina, what was the most challenging part of this project you did?
I think really understanding some of the more complicated topics like the CMB, where it just goes so deeply into things, and then understanding how, temperature fluctuations can lead to galaxy clusters and all those little nitty-gritty details.
Yeah, these are certainly very challenging topics, and kudos to you for diving so deep. Um, can you say a bit more about any next steps or future plans for exploring this further?
So yeah, the goal is to kind of find this particle. So right now, people there is a lot of research into finding the axion, but again, it's kind of really difficult to find because dark matter doesn't interact with much, so it's kind of hard to measure it. But the next goal would definitely be to find the particle.
Makes sense. Well, Serafina, thank you so much for this presentation
Thank you.
and helping us understand this topic better.